we are going to start today, that the nuclei part. Nuclei, and what you can tell, this is what is existing. The nucleus is existing at the center. If I'm just going to think that one atom, and nucleus existing at the center. So what in the nucleus, what the thing is existing? Lot of protons and neutrons, and the electrons are going to rotate around its nucleus with different speeds, and the expression of that things we have seen yesterday. In the last class we have seen what should be the expression of that energy, of that radius, of that velocity of the electron which are rotating in the different orbits, stable orbits. Okay, whatever. So now see what the thing is going to happen in the nucleus. In the nuclear physics, what I can tell is a nuclear physics. In the nucleus, protons and neutrons almost have the same mass. Almost have the same mass. Little bit. The neutron is little bit more. Little bit small amount of mass. Neutron is existing with respect to the proton. Whatever. So approximately we can take the same mass. So if the total number of proton plus neutron, that is called total number of nucleons. Total number of nucleons existing. So proton plus neutron, that is called mass number. Mass number is a number of proton plus number of neutron, just like this. Okay, so this is the thing. So now see, these are extremely small elements. So whenever I'm just going to think about the mass of the nucleus, or mass of the proton, mass of the neutron, this kind of thing, I have to just measure. What to do actually now? We have to take a new unit of mass, and that is called atomic mass unit. Atomic mass. Okay, AMU. Atomic mass units. Actually, you can see that atomic mass units is actually speaking, it is the 1/12 of the carbon atom. Which kind of carbon atom? Is the 1/12 of C12(6), this isotope of the carbon. If I just able to calculate this mass, 1/12 of the C12C, on the C12(6), this atom, we can have the value like 1.6603 into 10 to the power minus 27 kg, like this. So this is the atomic mass unit. See, 1.6603 into 10 to the power minus 27. With this, taking this as a unit, just we measure the mass of the neutron, proton, or the total nucleus. We just measure. Okay, fine, very nice. So now see that what to do from here. If we want to calculate that what is the density of the nucleus, if I want to find the nucleus. So actually speaking, we have to find the total mass number. What is the total number of proton and neutron is existing? Now, if I see that is A, but total mass number generally we denote by A, and atomic number. We take as the Z. Z is the number of proton. So A minus Z, this is the total mass number minus total proton number. Mass number proton plus neutron minus proton. So we are going to have this much of number of neutron. Okay, so this mass number and atomic number is important in this nuclei chapter. Okay, whatever. Now see, in this situation, if I want to calculate that what should be the density of a nucleus. Okay, now see, naturally, if I'm just going to have A is the mass number, this is the total number of nucleons, proton plus neutron in a certain nucleus, this much of total nucleons are existing. Okay, so now suppose some of the protons are there, some of the protons are there, some of the, these are the protons, these are the protons, these are the protons, some of the neutrons are there, some of the neutrons are there existing. So in this way, the total nucleus is going to get combined. Okay, so now in this situation, we can see if the number of this total proton plus neutron is going to increase, the size of the nucleus is going to increase naturally. So now let us think, just imagine it is a spherical shape, it's a symmetrical spherical shape, the nucleus. Okay, the radius is r. So what should be the volume? 4/3 pi r cube. Naturally, you can see the volume is going to increase with the number of A, isn't it? Natural thing. So we can observe that if I'm just going to find the total amount, the mass, so we can observe that we can have that if that mass will increase, that number of nucleon is going to increase, and if the total number of nucleon is going to increase, the radius is going to increase in that situation, isn't it? Radius will increase, naturally the radius is going to increase. Okay, so what the thing is that, what we can just conclude from here, we can tell that volume proportional to a, naturally volume proportional to a, naturally we can tell that, just if I just going to make a cube root, the r proportional to a to the power 1/3, isn't it? R is proportional to a to the power 1/3, isn't it? So now you can observe that if I'm going to have A is the mass number, the total mass will of the nucleus is equal to, if I'm just going to think that each and every nucleon is having mass m, the total mass m into A. If I want to find the density, so what to do? I have to just going to divide by the volume. This is the thing. So this will be the density. Isn't it? So now what thing is going to happen here? So if A/3 a to the power 1/3 proportional to r, so we can conclude that we can just have here, we can put a constant here. We can put a constant. We can put a constant. So we can put here just like this way, r is equal to r naught into a to the power 1/3. That we can put it. So we can write it here, m a divided by 4/3. Instead of this one, we can have r naught cube into a to the power 1/3. Tar cube mane shudhu a. So we just can have a cancelling out. So m by 4/3 by r naught cube. So you can see this r naught here is a constant though, because we have a relation like this way. Radius and a to the power 1/3 is directly proportional. Just we are going to put a constant term here, r naught a to the power 1/3. So we are just going to put that thing here, r naught cube into a. So a getting cancelled out. So what the result is going to come, the 3m divided by 4 pi r naught cube. So is the m is the mass of the nucleon, r naught is the constant number, 3 by 4 and pi, all these things are constant. So naturally the density of the nucleus, 3m divided by 4 pi r naught cube, this is the constant term. So any element, whatever may be there, it should be a gold, it can be a ferrous, it can be a hydrogen, whatever may be, doesn't matter. The nucleus have the same density for all the element, for all the atoms, because this is a fixed thing. Mass of the nucleon is fixed, R naught is fixed. Bas. So if I just going to calculate, if I am going to calculate this density, we can observe that it should be approximately in terms of 10 to the power 17. It should be 2.3 10 to the power 17 kg per meter. 2.3 into 10 to the power 17 kg per meter cube. This will be the density of the nucleus. It is so nucleus is a high dense region. All the masses are going to exist in that region of the atom, all the masses, a natural thing. Okay. Best. Now see, listen. So what the thing is that by atomic mass unit we can measure the mass of the proton, of the neutron, or any all the combination we can just measure. Okay. Now see, what the thing is that actually speaking, if I'm going to have A is the mass number, Z is the proton number, atomic number. So A minus Z is the number of neutron. Okay. So if the mass of the proton is mp and mass of the neutron is mn, so what should be the total mass of the nucleus? Just we can just use this one, Z into mp, because this is Z is the number of proton multiplied by the mass of the proton plus A minus Z into mass of neutron. So if I just calculate the mass, what is the existing mass in the nucleus, if I just able to calculate, this should be the net total mass, but we don't find this thing. So one thing, this is an important thing, that the expected mass of the nucleus is this expected mass, but we cannot find this thing. But if I just what is the amount of the mass we are going to get, that is the observed mass, just by observation, by measurement, actual measurement, what we are going to get. Suppose that is the m. That's the m. Suppose I'm just going to think that, and that is less than the expected mass. Understanding my point? So there is a lag, there is a shortage. There is a shortage of some mass, isn't it? There is a shortage of some mass. So where the mass is going to, it's going. So actually speaking, if I'm just going to calculate the what amount of shortage is existing, so we can see the change by shortage of mass. It's called a defect. This is called defect, mass defect. This is called mass defect. We can write like this way: Z mp plus A minus Z to mn minus m. This is the called mass defect. So this mass defect, which is vanished from the system, which is not just we cannot measure, we cannot observe, we cannot measure that mass. It is vanished. So where it has gone, this mass defect is getting converted to some kind of energy that is called binding energy. Called binding energy. So how this mass is getting to convert, is converting to the binding energy? Actually speaking, from the Einstein's theory, we know the energy and mass has a relation. We know that what energy, if the mass is getting converted to the energy, if the m mass is getting converted to energy, we can write this thing mc square. Suppose m mass getting converted to energy, so what amount of energy can be created? M into c square. C is the speed of the light in the vacuum. 3 into 10 to the power 8. So the mass into c square is equal to energy. So naturally, so if it is this is the defect mass, this is the vanished mass, this is the not existing in the nucleus. So in the what form it is going to exist? It is existing here in the form of energy. What kind of energy? Binding energy. So the binding energy is, we can write like this way, binding energy delta mc is a, so what means that? What is binding? What is the necessity of that binding energy? Why the binding energy is going to exist? It's the most important thing, that the binding energy is going to exist when you can see that these protons are positive, no? Positive, 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 positive. So in a very small region, these all positive charges are going to exist and they are going to repel each other. Electrostatics. Electrostatic repulsion. So who is going to bind all these things? Otherwise they will break, they will just go out. The nucleus will not become stable. The total, if the nucleus is not stable, atomic structure will fail. Simple thing. So naturally there should be some energy which is going to bind the nucleons, all the protons as well as the neutrons. This is the thing, binding. So this part of the mass which is lagging, that mass, which is the mass defect, that mass getting converted to energy, and it is acting as a binding energy to bind all the nucleons in the nucleus. So delta mc square is the binding energy of the nucleus. Delta m is the mass defect. I think children you understood. I think you're getting my point. Okay, so this is just if you understood the mass defects. Now see, the stability of a nucleus is dependent upon one factor that is called binding energy per nucleon. Binding energy per nucleon. Binding energy nucleon. Binding energy per nucleon. So what is that thing? If I'm just going to have that A is the mass number, total number of nucleons is A, then binding energy per nucleon delta mc square divided by A. What is the number of nucleons that exist? We have to divide that binding energy divided by total mass number. So binding energy per nucleons. If that any element, any atom, any element is having high value of this binding energy per nucleon, that nucleus is very stable. It is not going to just split easily. No. It is not going to split easily. It will not break. Otherwise, nucleus can break. That is called radioactivity. One thing is there. So automatically nucleus is going to break, and elements are going to change from the one element to another element. This is possible. But if the stability of that nucleus is high, definitely we can tell that that element is not going to change. It is a solid, but this is a very stable nucleus. In that situation, we can have a very stable nucleus. Okay, I think you children understanding. The stability of the nucleus is going to depend upon binding energy per nucleon. Okay, understanding? No problem. Very good. Okay, now see what the thing is that we have to understand how we can find this mass defect. How we can find this mass defect. Okay, definitely just we are going to see that how we can find mass defect. Okay, now see, if if I'm going to have one AMU, atomic mass unit, 1.656. 1 AMU, 1.656 into 10 to the power minus 27 kg. If I'm going to have this much, so what the thing is going to happen, if this much of 1 AMU is getting converted to the energy, then a delta M, this is my delta M, so delta M c square, so 1.656 into 10 to the power minus 27 into 3 into 10 to the power 8 whole square. So if I just calculate this thing, I'm going to get this thing in the joule. This is the energy form, joule. This much of joule, this amount of joule is going to get created. Now, you know, if I'm just going to divide the joule by the electronic charge, 1.656 into 10 to the power minus 27 divided by electronic charge, is that 1.6 into 10 to the power minus 19. 1.6 into 10 to the power minus 19. If I'm just going to divide this thing by the electronic charge, this energy is getting converted to electron volt. So EV 931.5 mega electron volt. Definitely this will be M. 931.5 mega electron volt. 931.5, this much of mega minus 10 to the power 6. So if I'm just going to convert one atomic mass unit into energy, we can get this much of 931.5 this much of mega electron volt. This much of energy I can get. Okay, fine, very good. Okay, now see what the thing is going to happen here. Now if we see that, if I just want to calculate, some examples, like if I want to calculate like for the C12 atom, if I want to calculate the binding energy, I want to find the binding energy of the C12. This isotope of the carbon. I want to find binding energy. So now how many protons are existing naturally? 6 proton, and we can have a 6 neutron. If I add this thing, I'm going to get the expected total mass. Okay, so now you can see that a proton is having mass 1.0078. Mass of the proton is equal to 1.0078 mu. U suppose mu and U. And mass of the neutron I can have that is also having value some 1.0087. 1.0087. So what is the expected mass of this one? 6 into 1.0078 plus 6 to 1.008. So this is the total AMU, total AMU of the mass. Okay, so just the value is going to come 12.099. 12.099 AMU. You can see this is a 12th. 12. So 1/12, this is the expected mass. This is the expected mass, but actual mass what we can get, because of the 12 number of nucleons is there. So one nucleon is one atomic AMU, isn't it? This is expected mass, okay, or actual mass. Actual mass is equal to 12 U. Okay, therefore just we can have the delta mass defect. It should be delta M. We can write like this way: 12.0990 minus 12, so 0.0990 U atomic mass. This is a change. This is the mass defect is going to exist in the carbon atom C12-6 isotope. Okay, so now we can have the binding energy. We can have like this way, delta mc square. Just if we do this thing, we will get that binding energy. So you know, for 1 mu, we know the 931.4, this much of mega electron volt will develop as an energy. So you can see for the mass defect of 0.0990 into 9.031, 931.4, 9.0 na 931.4 931.4 931.4 mega electron volt. This much of energy will develop. So we will get 92.2 mega electron volt. Just if I just multiply this thing, you will get 92.2 mega electron volt. This we can get. So naturally, this is the total binding energy of this C12-6 atom. Okay, so then we can observe that more and more binding energy, if the binding energy of a nucleus is more, we can see that if I just going to divide it by the number of nucleons, that will be the binding energy per nucleon. So if an element is having high value of that binding energy per nucleon, it is a more stable object. It will be a more stable object. So let us think that if I just going to calculate, if I'm going to compare ferrous Fe and Bi, their energy per nucleon. So what the thing is going to happen here? What will happen here? So let us think that we can have the ferrous. Ferrous is having like 5626, and Bi, this is another element. It is having 209 and 83, like this. So we are going to calculate what should be the binding energy per nucleon in the ferrous and in the Bi nucleus. So now let's think that we can see that this is the total number of protons. So ferrous, the expected mass of the ferrous will be, when the ferrous nucleus will be 26 into mass of the proton plus 56 minus 26 minus 30 into mass of the neutron. Okay. So if I'm just going to put the values here, mass of the proton and the total mass, and there will be a mass defect. What will be the mass defect? Minus m into f 56. This will be the mass defect. So we're just going to put all the values of the proton, just like proton having mass 1.0078. 26 into 1.0078 plus 30 into having the mass of the neutron, we can have 1.0087. 1.0087 minus of, we have just to find that mass of that total. So it should be approximately 55.93. If we just calculate, this should be actually 56 now. So we just can have the 55.9 approximately. This is atomic mass unit. So if I just going to calculate all these things, I'm going to have the mass defect due to the ferrous is going to exist. We can just approximately we can have 0.528 0.5284 0.5284. This is this much AMU. This much of effect is going to have naturally. So we know that just like 1 AMU equivalent to 931.4 mega electron volt. So delta mc square is equal to 0.5284 9.314 9314 dot. This much of mega electron volt. This much of mega electron volt. This is the thing, and we can have that delta mc square divided by total number of nucleons. One is 0.5284 into 931.4 divided by 56. So if I calculate this thing now, we can see that it is coming 8.79 mega electron volt. 8.79 mega electron. Yes. So this is the binding energy per nucleon for the ferrous. Okay. So now if we calculate for the Bi, the same process. How to calculate this thing? We have to find that. Like a total nucleon number is 209. So and total proton 83. So 83 to mass of the proton plus 209 minus 3 to the neutron minus 209 into okay. So this is the defect, mass defect. The similar manner, just what the procedure we have just followed in the previously, we have to in a similar manner we have just find what is the mass defect. We will find that 1.7608 1.7608, this much of atomic mass unit, this one. So you know, we already know that one atomic mass unit means 9314 9314.4 mega electron volt. So what should be the value? 1.7608 into 9314. This is the total energy created, this much of mega electron volt. Okay, this is the total mega electron volt. This is some energy, binding energy, delta m c square. So what should be the binding energy per nucleon? Delta m c square divided by total mass number, mane 209. It is going to come 1.7608 into 931.4 divided by 209. So by calculating this, we can find that it is going to come for Bi nucleus 7.85 mega electron volt. So in the comparison to the ferrous Fe, Fe is having 8.79 mega electron volt, but Bi is having 7.85 mega electron volt. So naturally, per nucleon, ferrous Fe is having higher binding energy. So ferrous is more stable. Actually, ferrous is the stablest, most stable nucleus. Most stable nucleus. This nucleus is anyway, it will not going to break. There is no chance that the ferrous is going to show radioactivity. Ferrous will not show radioactivity. Its nucleus is not going to break. It is the most stable. I think children, you are understanding, okay, isn't it? Very good. Now, see, whenever that total number of proton or neutron in the nucleus is going to increase, we can see that binding energy per nucleon is going to decrease. So with the decrement of the binding energy, the nucleus is going to become unstable, or there will be a probability, there is a chance that nucleus can break. Okay, so that phenomenon is called radioactivity. So in the radioactivity phenomenon, whenever the nucleus breaks, some radiations come, some elements come. So first element is the alpha particle, second element is the beta particle, third is not a particle, that is a electromagnetic wave, that is called gamma ray, gamma wave. Okay, so alpha, beta, gamma, these are the things, when a nucleus breaks, these things comes out. Actually, alpha is the helium nucleus, doubly ionized. Okay, so what the thing is going to happen? Why this is alpha? You can see the helium is having 2 protons, 2 neutrons. Okay, so whenever I'm just going to have the 2 protons going to exist, 2 electrons are orbiting in the orbits, isn't it? So naturally, when if anyway the 2 electrons has gone out anyway, that helium is going to become ion, is a pure nucleus, not atom, ionized condition. So this situation, the helium nucleus is alpha. The helium nucleus clumps out. So any element, whenever it is just suppose X, it is having a mass number A, atomic number Z. If it emits alpha, we can observe that its mass number is going to decrease. What is the amount? Suppose it is created Y, another element, we can see that the Y having a mass number A minus 4Y, because helium is having 4 proton, 2 proton, 2 neutrons, total 4, so A minus 4, and it is having, this Y is having 2 less atomic number, print minus 2. So this thing will happen whenever the alpha emission occurs. Similarly, this beta particle is actually electron. So how the electron is getting created? This is the electron, is not the electron of the orbits in atom. No, don't get confused. Atom having some electron in its some stable orbit, which electrons are rotating. But this electron is not that electron. No, whenever emission from the nucleus is going to occur, beta particles is emitted, that are also electrons, but that electrons are not that orbiting electrons which is rotating around the nucleus. So how these electrons are produced? How the beta particles is produced? Actually speaking, if one neutron breaks, it creates a proton plus electron. Proton is positive, electron is negative. This thing happens. Yeah. So what thing will happen here? So whenever neutron breaks, by splitting the neutron, this electron is going to come out and proton will exist. Proton will exist in the nucleus. Okay. So now if this X is emitting some beta particle, we can observe that it is having a mass number and atomic number this much. We can observe it is created this much. So you can observe that this is a mass number is going to remain same because the neutron is converted to proton. Mass number is not going to change. It is a, but atomic number is, because the number of proton is going to increase. So Z plus 1. This thing will happen. Okay. And that electron is not going to exist in the nucleus. It is going to come out. It is going to come out. Okay. This thing is going to happen here. And after emission of the alpha and beta, whenever the emission of the alpha and beta has occurred, we can observe that due to this emission, the total nucleus has become unstable. Actually, nucleus having in a state of the ground state initially, but due to the excess binding energy for what we can tell, this is an unstable nucleus, less amount of binding energy, it breaks, nucleus breaks, and emission starts, radioactivity starts. And whenever the radioactivity starts, emission starts, what the thing is going to happen? Nucleus becomes unstable. So now after emission of alpha and beta, to make the nucleus stable, to make the nucleus in a ground state, stable ground state, some emission, some energy has to be radiated. In the excited state, when the nucleus in the excited state, nucleus has to emit some radiation, that is the gamma radiation. So after emission of the gamma, whenever the gamma comes out, that nucleus is going to become stable. So suppose X, A, Z is emitting gamma radiation. It is not a particle, it is an electromagnetic wave. The same thing exists. Okay? But it is a stable nucleus. After this was the excited nucleus, unstable. After emission, it is unstable. Okay, so this is the just simple thing, how by the emission of the alpha, beta, and gamma happens in the radioactivity. Okay, so now that thing is that some laws of the radioactivity is existing. You see, whenever an element, atom becomes radioactive, element is going to become radioactive. Okay. What the thing is going to happen in that situation? It emits alpha, beta, gamma. This is the thing. And what the thing is going to happen? Due to the emission of the alpha, due to the emission of the beta, due to the emission of the gamma. So, due to the emission of the alpha, beta, and gamma, new elements are created. New elements. So, naturally, you can see that, observe that if that N is the total amount of atoms existing in a nucleus, in a not nucleus, in a substance, total number of this decay starts, disintegration starts. Due to the radioactivity, this breaks, nucleus breaks, and new elements are developing. Okay, so now rate, what is the rate with which decay starts, disintegration start, rate of change of n with respect to time, according to this law, we can tell it is directly proportional to n. The number of atom existing undecayed, more and more number of atoms existing undecayed, the rate will be more. Okay. So now we can write like this way: dn dt is equal to minus lambda into n. What is this minus lambda? What is this thing? It is called a decay constant, disintegration constant. Lambda is called the disintegration constant of that element. Understanding my point or not, children? I think you understand, isn't it? Okay. So now what the thing is going to happen, dn by n is equal to minus lambda dt. So make the integration both sides, because lambda is a constant, disintegration constant of that element, is a property of that element. So naturally I'm going to have log n is equal to minus lambda t plus something constant k. By integration, which is going to have like this kind of expression. So now if I'm going to put T0 means when we started our observation, at the instant when we started our observation, then the T0, then at that instant of time, if I see that the initial number of molecules is n0, let us say that at T is equal to 0, n is equal to n0. So we can have log, when I'm going to put the t is equal to 0, I'm just going to put the n0 is equal to minus into 0 plus k. So the value of the k, I can have log of n0. So n0 is the undecayed number of atoms existing when we started our observation. When we started our observation at the time t is equal to 0, time t is equal to 0, when we have started observation, this is the number of atoms existing undecayed form, pure form. There was no decay and that's, but whenever we started, after the time increasing, decay starting. Simple, isn't it? So now see what the thing is going to happen. We have just got the form of the expression of the k here. So we are going to put the value of the k here. So we can write like this way: log n is equal to minus lambda t plus log n0. Instead of the k, we are going to put this value. Okay. So now we can write like this way: log n minus log n0 is equal to minus lambda t. So we can write like this way: log of n by n0 is equal to minus lambda t. Okay. No problem. Fine. Now see, we are going to express this thing. So e to the power minus lambda is equal to n by n0. So final expression of the variable n, that variable n is equal to koto n0 into e to the power minus lambda t. Simple formula. Simple formula. So this n is what? The expression, it is the multiplier of the e to the power minus lambda t, n0 into e to the power minus lambda t, that's the n, isn't it? Isn't it? Understanding my point? So you can see that I can write this n n0 e to the power minus lambda t, mane 1 by e to the power lambda t, 1 by e to the power lambda t. So you can see whenever the time is increasing, the denominator part is going to increase. Whenever the denominator part is going to increase, n0 by bigger denominator, the value of the n is going to decrease. Understanding my point? The time increasing, n is decreasing. Mane, n is what? N is the number of atoms undecayed form. This is the atoms, number of atoms which has not decayed still after the t time. After the t time, still not decayed, still not disintegrated. It is not get converted to other elements. Understanding my point, children? So this is the thing. This is a basic expression, basic formula for the radioactivity. Okay, so now at this situation, if I'm going to think that we want to find such expressions, it will be little bit easier to find the condition up to the what point the disintegration has occurred. Up to what point the disintegration has occurred, just we want to see that. So now suppose that if I'm just going to see that half, I'm going to think about that half part of the total number has decayed. Half part. Suppose initially n naught was the existing, it has become half. So what we can write from here, n naught divided by 2 is equal to n naught e to the power lambda t, isn't it? So n naught cancelling out, so we can write 2 is equal to e to the power lambda t. So both side I can take the log 2 is equal to, if I take the log, the lambda t is going to come, because log of e with the base e, it is going to become 1. So now the t is equal to log of 2 divided by lambda. This is called half-life. This is called what? Called half-life. Means what? Half-life means what? Half-life means it is a particular duration of the time. This is a particular duration of the time when total n naught is going to become n by 2. কি হবে? তাহলে আমাকে জানতে হবে এখানে কি disintegration constant. What the information is important. Log 2 we can put this value, but if I know the disintegration constant, immediately we can put it here and we can find the half-life. ঠিক কি না? Understanding everyone, isn't it? Very good. So now if I know the half-life, and suppose half-life is t, suppose t is the, if I use a half-life, ঠিক আছে? Now, so how the graph is going to come, if I'm just going to draw the time versus n is the number of atoms radioactive. Initially I'm going to think that n naught, okay, n naught is the initial undecayed number of atoms. So if this is the t, another t, I'm going to think about after 4 slots of half-life, what is the amount, what is the number of atoms in a undecayed form existing? Check, no problem. Now see, first half-life, graph is going to come. What is this saying? This value is what? n naught by 2. Simple thing. So what is the remaining? If the n naught by 2 decayed, n naught by 2 is existing. Okay, very good. Acha, for the second half-life, what is this saying? n naught by 2 means n naught by 4. Understanding? No problem. Very good. Okay, now third half-life, this point. What is this point? n naught by 4 into half, means n naught by 8. This point. Understanding, children, my point? So, and the last one. What is this value? This value n naught by 16. Simple thing. No problem, no jhavel. Okay, so if I'm just going to draw the graph, undecayed atom and the time, and I'm just going to take the half-life as my period, I can observe after 4 half-lives, the total undecayed number of atom is going to become like this way. 1/16th of the total amount of the tomar undecayed atom. It is good. So how many amounts? So after 4 half-lives, how many atoms has decayed? If the question comes, so what is the 15 and not by 16? This is the amount has decayed. This has converted to other form of atoms, other elements. Only this is and not by 16. This is the element existing undecayed form. Okay.